Today we will prove the following important theorem due to Emil Artin. So the statement is the following. Let K be any field, K be a field, and gamma be a finite subgroup of the group of automorphisms of the field. Okay, be a finite subgroup of the group of automorphisms. Then recall we talked about the fixed field of K, which is a set of all elements of K which are fixed by every element of gamma. Then K colon K gamma, that is the degree of this extension, is finite, and in fact it is equal to the cardinality of this subgroup gamma. Okay. So recall the finiteness of this extension is also part of the theorem here. Okay, and this theorem is rather important. It will play an important role in the further development of Galois theory as we go along. Let's prove this theorem. We already established one important ingredient of the proof, which is the linear independence of characters. Okay, so that's what's going to be used here. So let's prove, let's set up some notation first. So let me call this fixed field as F. So let F denote the fixed field K gamma, which is the set of all elements of K such that sigma A is A for all sigma and gamma. Okay, and recall it's a subfield. So let's look at the extension K over F, and we will establish the theorem in two parts. We will establish inequalities in both directions. Okay, for the dimension. So let's say first claim is going to be that the cardinality of gamma is at most the degree of the extension. Okay, so this is the first claim, and then claim 2 will be the reverse inequality, that the degree of the extension is at most the cardinality of gamma. So we'll prove this using the linear independence of characters. So first observe, if the degree of the extension is infinite, then of course this is trivially true. There's nothing to do. Okay, is infinite, then we are done. Okay, because cardinality gamma is finite, the area size is infinite, there's really no content there. So let's assume, so therefore we may suppose that the degree of this extension is finite. Okay, so it's a finite extension. So we'll make that assumption. Okay, now recall the following, that the space of automorphisms, the group of automorphisms, is a subset of what we call maps KK, a set of all, this is just all set maps, just functions from K to K. Just map of sets, no further structure. And we said that this is of course a vector space. This is a vector space over K. And as a corollary to our proof of linear independence of characters, we said that the space out K is actually a linearly independent subset. So this is a linearly independent subset of this K vector space maps KK. Okay. Now, so what does that mean? When I have a vector space and I have a linearly independent subset inside this vector space, then, let's look at gamma, in fact, because that's what we are interested in. Let's look at gamma, which is a sub of a linearly independent set. So gamma is also linearly independent. Okay. So clearly the elements, the automorphisms in gamma subset of maps KK is also linearly independent. And in particular, this implies that if I take a subset of, if I take a subspace, so any subspace It's called U of maps kk, which contains gamma, has dimension at least, so satisfies the following property, that the dimension of U must be at least the cardinality of gamma, right? Because gamma is a linearly independent subset and U is a subspace which contains it, so the dimension of U is definitely more than the dimension of gamma. Okay, so that's going to be our approach. We are going to try and prove this inequality by producing a subspace U inside maps kk, which has dimension equal to the degree of the extension. Okay, so the right hand side will be realized as the dimension of some subspace of the space of maps. So that's the idea, and in this case it's not too hard to construct this subspace, in fact. So so recall K. So what are we thinking of K as? K is an extension field of F, but that in particular of course means that K is a vector space over F, and of course we also know its dimension, which is what's called the degree, dimension equal to K colon F. And recall, to start with, we assume that this is finite. Okay, so therefore this is in fact a finite dimensional vector space. K is a finite dimensional vector space over F, and therefore the subspace, well, let's look at the following subspace. For the moment a subset. Let's define U to be, well, the set of all maps. Think of it as the set of all maps F from K to K, set functions which satisfy an additional property that F is a linear transformation of K thought of as a F vector space. Okay, so F is F linear. Okay, so it's a linear transformation from K to K when you view K as an F vector space. And of course this is the canonical standard notation for this. This is just the end Fk, the space of all F linear endomorphisms of the vector space K. Okay, so I'm going to define U as this. Clearly U is a subset of maps kk. And let's check the following properties of U. Firstly, U is in fact so maps kk is a K vector space. So claim is that U is actually a subspace. So just to emphasize that now we are talking the vector spaces are over K now rather than over F. So recall, right now we sort of have both things. There are vector spaces over K which we are looking at. There are also, K itself is thought of as a vector space over F. So let's just make things clear by, I just put a K there to say that I'm thinking of U as a subspace of the K vector space maps kk. Okay, so I claim firstly, so here are some properties. Claim U is in fact a K subspace of the vector space maps kk. Okay, so that's in fact rather easy, because, well, what do elements of U look like? So if I have F1 and F2, two elements of U, so I need to ensure that they are closed under addition and it's closed under scalar multiplication by K, right? So what should I do? First let me check if it's closed under addition. I take F1 plus F2 and I ask, well, how does it, what's the value at A? It's just F1A plus F2A. And of course we know that sum of two linear transformations is automatically a linear transformation. Okay, so that's the definition, and this is, one can easily check that F1 plus F2 is F linear. It's again a linear operator. Okay, so this is the easy part. The part that's somehow not immediately obvious is if I take an element F in U and I take a scalar lambda from K, okay, not lambda from F but lambda from K. So you already know that if you take a linear transformation, linear operator on a vector space, if I multiply it by a scalar from the base field, then of course what I get again is a linear operator, right? If lambda comes from F, lambda times from the base field F, then lambda times F, so small f here, lambda F would of course automatically be a linear transformation. Okay, but I want to claim that if I take lambda in K and f in u. Okay, so let's maybe do this in the next page. So we need to actually check this to ensure things are okay. We take any element of k, and for all lambda in k and for all elements linear operators f on k, we need to check that this lambda f is again a f linear operator on k. Okay, and why is this true? Well, because just from the definition. Okay, so this is true because just see what lambda f does to a. You first evaluate f on a, that's now an element of k, right? Because f was a map from k to k anyway, and now you multiply that element of k by this other element of k, which is lambda. So it's just multiplication. And now this new definition, this lambda f, why is this f linear? Well, you have to check that if I put, if I put a plus b, then I will get a plus b on the other side. But well, it's more or less, I just have to multiply by lambda anyway afterwards. And f was linear. F was linear over the base field. And similarly, if I take lambda f and I need to check linearity over the base field. If I multiply it by some element mu from the base field, so now mu is from the base field f, lambda is from the bigger field k, I need to check whether I can pull the mu out. Okay, so first by definition, this is lambda f of mu a, and the map f is a linear transformation which is f linear, right, over the base field. So I can pull the mu out. So this is now lambda mu f of a, because f is actually in end of k. So I can pull out scalars from f. Okay, so what this says, so like I said, it required a little checking, but it's still a very simple fact that if you multiply by lambda coming from k, what you get is still a f linear transformation. Okay, so that checks the first claim that the subspace U is actually a k subspace. Property 2, let's check that U actually contains gamma. Okay, so recall that's how we are going to prove the dimension bound. Why does U contain gamma? Well, what is U and what is gamma? So recall U is just a set of all f linear operators on k. Gamma is some subgroup of the automorphism group, and the key definition here, f is actually the set of fixed points of gamma. Okay, so why does U contain gamma? Well, we just have to check that. So to check this, I need to check IE. So what does this statement say? IE, if we take any element sigma and gamma, sigma is actually a linear transformation from, I can think of sigma, so sigma is actually a field automorphism, but sigma is actually also a linear transformation from k to k with linearity over the base field f. Okay, so why is this true? Well, let's check the properties. So sigma of a plus b has to be sigma a plus sigma b, but that is true because sigma is a field automorphism. Okay, because sigma is it's in gamma, so in particular it's a field automorphism. Property 2, if I take sigma and I multiply a by an element mu is a scalar from f, then I should be able to pull out the mu. That's what linearity means, right? But now this is the same as sigma mu sigma a. Again, for the same reason, sigma is a field automorphism, but now sigma of mu is actually mu again. Okay, and why is this? This is because sigma is actually in gamma, okay, and mu is in f, which is the fixed field of gamma. Okay, so that means that sigma certainly fixes mu. Right? Sigma mu must be mu because mu is coming from k gamma. So that is the key thing to check there. Okay, and so that means the mu can be pulled out. It really came out as a sigma mu, but sigma mu turns out to be mu in this case. Okay, so we have actually checked both properties that sigma is required to satisfy in order to be a linear transformation. So we've also done this. So we have sort of done what we set out to do, that U is we have constructed a subspace U which contains gamma. Okay, and the subspace, the obvious one here, the set of all F linear endomorphisms of K viewed as a vector space. But then finally, here's the thing. U is actually finite dimensional. U is actually, recall we said U is a K vector space, but in fact its dimension over K is finite, and it's actually equal to the degree of the extension, the dimension. So this is the dimension of K over F. Okay, I mean it's actually equal, but we don't need the full force of that, so I'm not going to bother proving it. I'm just going to show you that the dimension of U is at most the dimension of K over F. Okay, and I'll sort of leave the proving of the reverse inequality as an exercise. We won't need it for the proof itself. Okay, so this is the third and important claim, that the dimension of this space U is at most the dimension of K over F. Okay, now this requires a little proof, so let's prove this. So what was U? U was the space of endomorphisms, and let me try and construct for you a spanning set of U, okay, which has cardinality equal to the dimension of K over F. So how are we going to do this? So let's pick alpha I from 1 to D be a basis of K over F. Okay, basis of K as a vector space over F. Okay, so recall we have already assumed that K over F is a finite dimensional vector space. So let D denote the dimension of this space. So for me here D will be just the dimension of K as a vector space over F, in other words. Okay, so I take a basis and let's construct, let's look at its what we call the dual basis, right? So for these alpha i's, corresponding to the alpha i's, I have maps Fi. So what are the Fi's? 1 to D. These are elements of the dual vector space. Okay, so let this be the dual basis. So what does that mean? So recall, dual basis, given a basis you can construct its dual basis of linear functionals. So i.e., what are the Fi's? The Fi's are linear functionals on K. In other words, they are maps from K to the base field, right? The field, remember, is F here. So Fi's are maps from K to F, and they satisfy the property, I mean they are linear, such that Fi is linear functional, it's F linear, and Fi evaluated on the basis elements gives me 1 or 0. Okay, so this is 1 if I equal to j, 0 if I not equal to j. So this is what we call the dual basis corresponding to a given basis alpha. Okay, so now what have I done? I have constructed D elements called Fi's, which are all maps from K to F, but I will now think of these as maps from K to K. Okay, so what shall we do? Let's call Fi tilde. Let Fi tilde be the following map. It's a map from K to F composed with the inclusion map from K to F. So let's do the following. Take Fi, and this is just the inclusion map. The composition of these two things we will call as Fi tilde. Okay, so what is now Fi tilde? It's become a map from K to K. It's just the inclusion composed with Fi. Okay, and observe, this is a composition. The inclusion map is also a linear transformation of these two F vector spaces. So think of everything here as being an F vector space. Then Fi is F linear, inclusion is F linear. Therefore, this composed map that we have constructed should be thought of as a map from K to K, which is F linear. Okay, in other words, Fi tilde is an endomorphism of K over F. Okay, so these are, we are almost there. We now have a bunch of maps. Our claim is that the subspace U that we are looking at is spanned by these fellows. So U is just the span of these D elements, Fi tildes quantity. Okay, so U was what? U was just a full set of endomorphisms. The claim is these D endomorphisms are enough to span the whole space. But now recall, everything is, so now I have, I'm again switching fields. I'm thinking of U as really a subspace of the space of all maps from K to K, right? And so these are all, and we have already shown that U is a K vector space. So I claim that over K, thought of as a K vector space, the span of the Fi tildes will actually give me everything. Okay. So observe, this won't happen over F, because if I have, so quick aside, so suppose I have a vector space V over the field F. So I'm saying, okay, suppose I look at the space of all endomorphisms over the base field from V to V. We know the following, that this has dimension. So the dimension of this space is D square, right? Because, well, what's D? D is the dimension of the ambient vector space V over F. Okay, so if V has dimension D, then the space of endomorphisms is like the space of all D cross D matrices, right? Remember, linear transformations and matrices are the same thing. And so this is like the space of matrices which has dimension D square. So over F, this has no chance of being true. I am claiming it's enough to just have D elements. These particular D elements will give me everything when they span. Okay, and the reason why this works is because this is actually over the bigger field K. So we are claiming if you take the bigger field K, then these D elements are in. Okay, so let's prove this. So once we identify the right elements, the proof itself is easy. So let's take a linear transformation. So let's take T from K to K. T belongs to U. In other words, T is a K F linear endomorphism of K. It's U. I need to show T can be written as a span of these elements. So let's look at what T looks like. So T of an element X is just, so I first write the element X as a linear combination of the basis elements alpha j. Okay, and now what are the xj's? Xj's are all elements of the base field F. Okay, because the alpha j's form a basis of K over F. And now this is just summation xj T of alpha j. So equals to T. And now let's call T of alpha j as a new element of K. So T, what is T acting on alpha j? Well, it's just going to be some other element of K. Right? So let me call this element as beta j. So this definition, beta j is this element, and that's of course an element of K. Okay, and now this becomes the sum beta j xj. K goes from 1 to T. And now what is xj? We call xj is just what you get. So xj is just the coefficient of alpha j in the linear combination. This is just the value fj tilde of x. Okay, and why is that? Because of the way it was defined. So if you recall what the fi's were, they take value 1 on alpha j. I mean, fi takes value 1 on alpha I and 0 on everything else. Well, fi tilde is the same thing really, right? The same as fi, and then after that you just take the inclusion into K. So it doesn't do anything new. So fi tilde is, well, it's just going to first map alpha I to 1 and all the other alpha j's to 0. That's what fi tilde does. And so if you ask what is fj tilde on x, well, you apply it to this linear combination, then it will kill all the other alpha i's except for the jth one. Okay, so this is the usual property of dual bases. Okay, very good. So we just look at what we have shown finally. This just means we have shown T is just this linear combination beta j fj tilde. Okay, and that's exactly what we set out to prove. And the key point, recall here, is that beta j's are now elements of K, not necessarily elements of F. Okay, so that's really what makes the proof work. So this means that T belongs to the K span of the Fj tildes. Okay, so what does that give us? It proves the following. It shows that, therefore, so let's look at all the three facts. So we have shown firstly that, so okay, let me just write this out. So this shows, finally shows that dimension of this space U is at most the degree K colon F. Okay, so having shown that this is at most the degree, what does it give us? It says that so and together with the other two facts, so let's also write, this was the third fact which we have now proved, and recall facts 1 and 2 said, fact 2 said U contains the space gamma, the set gamma, and U is a K subspace. Okay, so between these two we conclude that the dimension of this space U, whatever it is, must be at least the cardinality of gamma. And the first condition says that the dimension of U is further bounded above by Kf. Okay, so finally that proves exactly what we set out to prove, that the degree of the extension is always greater than or equal to the cardinality of gamma. Okay, so that's one part of the proof. So let's go back here. So the theorem, we have shown claim 1 of the theorem. Okay. Now we'll prove claim 2 in the next video.